Hi, welcome to another video, PiPad Mathematics. I'm Professor Lamb, and I'm going to do a little video here that is along the lines of the work of Mark Driscoll and his team, and kind of growing squares and then growing towers, and you got growing squares. You got a lot of geometric shapes that you can help build algebraic understanding and algebraic reasoning, algebraic thinking. His work is fostering algebraic thinking, FAT, so it's real fat, pretty hot and tempting. Anyway, that's an old school show. Anyway, and I apologize for any noises in the background. Got cars driving on the road, dogs barking in the background, but I think you can hear me hopefully okay. Now I'm using an app here that you can build blocks on, and you can build them in this kind of dimension, this view, this skyward view. You can take I can take the eraser here and I can say remove that block, and then I can add my pencil and I want to put a red block right there. And you have to do a little bit of thinking as a teacher, preparation, and getting it set up so that you can then get into the 3D realm of kind of walking in, and it's got kind of the controls of moving around. Like this one's going to go looking left and right. This one's going to go forward. I need to go and left and right and around, and then I'm going to kind of turn around and look at kind of what is built there. And if you notice, I'm missing a piece up there at the top, so I'm going to go back and fix it. So I'm going to go back over here, and I need to put a red piece on the top right there. Now I go back to my virtual world here. I need to turn around, and there we are. Go forward, turn sideways, kind of go back a little bit, over this way, turn a little bit, and then kind of there you have it. So here we are, 3D world, sets of staircases, and this illustrates the problem. Now from this you can ask a number of questions of students. Here are this is the first, the second, the third, the fourth, and then the fifth iteration of our growing staircase here. And we can ask the question, how many blocks would be in the sixth? How many blocks would be in the 10th one if this continued? How many would be in the 20th one? And then you can also do things related to the kind of back into the checkerboard effect, the red and the yellow. You can ask, well, how many red ones are in there in your growing staircase? How many red ones would be in the 10th staircase? How many red ones would be in the 6th staircase? How many would be in the 100th staircase? And what this does is it develops or it gets students to start thinking about a rule. And so what I'm going to do here is I'm going to kind of see if I can go straight on, kind of take a picture. What I like about this app is you can build it, and then you go in and you get ready to do some analysis. Now, of course, the app is not really built for teachers, probably not built by teachers, but we have this ability to build it, construct it. Then I can take it. Oh, that was loud. I can take a screenshot. I'll edit that out. So I can take a screenshot, and then I can open up Explain Everything, an app that I should have up right here, and I open up a new page, and we can insert new picture from existing photos. Come here, here's our existing photo, hit done, and there's our photograph of what we had built. And we pose the question, or we ask the question, how many squares would be in the fifth square? Well, that one's fifth's already counted, but if you only had these four, let me go ahead and write, well, this is the first step, staircase, that's the second staircase, and the third staircase, and the fourth staircase. So how many would be in the fifth staircase? Well, students can draw it. They can come over here and they can draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Did I count that right? It's 9. That should be 12. 13, 14, and 15. Did I count that right? So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So in the fifth one, we have 15 pieces. I make a table of values. So staircase, so I'll put S for staircase, and then B for blocks. That's a B, not a 13. And staircase 1, we had 1 block. Staircase 2, we had 3 blocks. See, 1, 2, 3. Staircase 3, we had 6 blocks. Staircase 4, we had 10 blocks. Staircase 5, we had 15 blocks. But the question is, what if we went to the 10th? Or what if we went to the 100th staircase? What if we went to the 1000th staircase? And in order to do that, we're going to need some kind of rule, some kind of way of explicitly implementing or inputting or calculating with these independent variables, these plug-in numbers, the ones that are going to be put into our function, our explicit rule. And once we have that rule, we can plug in 10, we can plug in 100, we can plug in 1,000. So how do we come about this rule? How do we understand what this rule is? And sometimes it's guess and check. Sometimes it is, well, I have 1 and I get to 1, and I get 2, I got to 3, 3 got to 6. For the most part, I'm increasing, so I need to do something that gets it bigger. Well, I can add and get things bigger. I can multiply and get things bigger. I can square it. I can raise it to an exponent. I can do all these things, and it grows. It gets, the numbers will get bigger. So that's an understanding of mathematical thinking that's important. And we see if we can do that constantly. Well, 1 to 1, you didn't really add anything constant, because 2 went by plus 1, 3 was plus 3, 4 was plus 6, 5 was plus 10. Oh, we didn't quite get it that way. And now we need to see, well, what about, we could look for patterns this way. Well, that's the difference of 2, that's the difference of 3, that's the difference of 4, and that's the difference of 5, which makes sense because we added these down at the bottom. We added that bottom row of 3 to the 2. You see how the 2 one is sitting right up on the top there? 2 is sitting right here, and so we added the 3 down there. And then we added these 4 to our third staircase. So this third staircase is sitting above that line, and we added 4. So it makes sense to add 2 plus 3 plus 4 plus 5. And then these differences are 1. And algebraically, this is second order difference was constant. So therefore, if the second order difference is constant, then we're dealing with a quadratic. And we can algebraically go through and figure that out. It comes down, algebraically, you'd have to use ax squared plus bx plus c, then go in and do what would be the next differences be. So we don't want to go there. We're looking more in the lines of getting students to not just know a rule to find it, but to find some way maybe to graphically, visually see how a rule could be developed from this. And one way to do it is to take our original, and if we drew kind of a square around it, then we would have a perfect square. But we have too much. If I were to take 5 squared, I would get 25, but I only have 15 in there. So I have 10 less than 25. And over here, if I were to take my 4 squared, I would be 16, but I have 10. So now I have 6, or I have 10. I have 6 fewer than 4 squared. So there's this idea, well, I could square it, but then I got too much. Well, if I square it, if I don't want to have too much, then I could actually divide that square in half, If I divide that square in half, then I'm closer to what my actual drawing is, or what my actual staircase is, and that's good. So 5 squared, or if I square the step number and then divide it by 2, I'm pretty close to what I'm needing. And then we got to go with our 5. What about these 5 little triangles that are sitting on top of that part we didn't count? And so those are 5 half squares. 5 half squares. And we take that, and we know there's 5 of them. So we took our 25 divided by 2, which was the 5 squared divided by 2, and then we add 5 divided by 2. Okay? So we took our 25 divided by 2, and then we added our 5 divided by 2. Because these are fractions with the same denominator, we can add those, so that gives me 30 divided by 2, which is 15. And that is the number that we got right there. And if we did this same rule being we take our step S, and we square it, then we divided it by 2, and then we added S, the step number, because divided by 2. Because S was how many were in that diagonal right there. S was how many? There's 3 on that diagonal. There's 2 in that diagonal. There's 4 in that diagonal. So we got S squared divided by 2 plus S divided by 2. That gives me 15. Now, we can leave it like that. We're good. Kids figured it out. Hey, I got it. I got a geometric way. I got a picture way. I'm going to take S squared divided by 2, then add S divided by 2. And I'm done. And I'm okay with that. Got to Dallas. The students figured out how to solve the problem. I'm fine with that. But if you want students to go a little bit farther, a little bit, older students, or even you can wow and amaze your younger students to say, I'm going to show you how we can actually make this simpler. I'm going to, because they're the same denominator, take my S squared and then add S and divide it by 2. So you take your step number squared plus the step number, take that answer and divide it by 2, and you'll get the same result. Let's test it out. If I took 5 squared, hey, 25, plus 5 is 30. 30 divided by 2, 15. Boom, got the answer. And then you can wow them some more with some algebra. This is great stuff. We're going to go in and we're going to say S squared plus S. Well, there's an S in each one of those, so I can actually undo the distributive property, and I'm left with S times S plus 1. That looks like a 5, doesn't it? That's an S. 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 So S times S plus 1 divided by 2. So you take the step number, multiply it by the step number, or one more than the step number, and divide that by 2. And this thing looks a whole lot like that rule we got when we were adding 1 plus 2 plus 3 plus ... plus n, if you will. When we were adding up the consecutive counting numbers, this was the rule that we came up with. Of course, we used an n times n plus 1 divided by 2. But if you take any number, or the number of consecutive numbers you're adding, counting numbers you're adding, multiply it by 1 more than that and divide by 2, you get the sum. And that's the same thing here. And that's actually all inside of this drawing right here. Because this drawing right here shows you I have 1 plus 2 plus 3 plus 4. So each layer on the steps is your counting number, or are your counting numbers. So 1 plus 2 plus 3 plus 4, you go plus 5 plus 6 plus 7 plus 8. So all of this to say that you have growing squares like that, or growing staircase or staircase problems going to result in S times S plus 1 divided by 2. And that's one problem that you can do with this. Another problem that you can do with this, we'll bring that picture back in, existing photo right here, yay, hit done. Another problem that you can do with this is you can say, hey, let's just count the red ones. Oh, math people are so crazy. We want to just make things a lot more challenging and difficult than they have to be. But that's what thinking is. Life is about difficult challenges. Life is about solving problems that come about that you're not used to, that you're not accustomed to. And good problem solvers really make a difference in life. And that's what we as teachers of mathematics are challenged to do, to get students to think. So we pose questions. What do we pose? We pose questions like, all right, how many red pieces are going to be in the fifth step? And I'm going to number the steps. 1, 2, 3, 4. So how many are going to be in the fifth step? So I'm going to, whoops. Let me shrink that down. We could draw a picture. Hey, we did that already, right? We can draw a picture. There's 5 there. Watch that. 5. There's 4 there. There's 3 there. There's 2, and then there's 1. And you look at it like that, and you're like, well, Professor Lamb, that's good stuff, but you don't see all the blocks. And you're like, you're right. I shouldn't do it like that. So I'm going to take all of that, and I'm going to erase it. And let me do that again. And so we're going to draw 5 here. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3. 1, 2, and 1. Alright, so we got our staircase. Not at all drawn to scale. Should have taken a little bit more time, but we got it. Okay? And we're trying to draw how many red ones are going to be in there. Well, it looks like the ones on the diagonal are red. So this is going to be red, and 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 this is going to be red. Good. And then it looks like we got the red ones on the diagonal, and then it looks like it skips a diagonal. So we skip that diagonal, and then we go red in the next diagonal. So this is going to be red, this is going to be red, and that's going to be red, and then this one, that last diagonal, is going to be red. So it's at every other one. So we did it. We can count them. There's going to be 5 there, 6, 7, 8, 9. So that's 9 red ones. Well, how many are going to be in, I don't know, the 14th? How many are going to be in the 14th staircase? This one is the 5th staircase. So how many red are in the 14th staircase? I need a pattern, don't I? I can draw it, sure. It may take me a little while. Will I get to Dallas? Will I get to the solution? Sure. We'll do that. But I need a rule, or I need some way of figuring it out. And so you stare at this a little bit, and then you notice this pattern. You notice this pattern of those diagonals. And you look at how many are in there. So in the second one, there's 2 on that diagonal and then none. On the third one, it's 3 and then 1. On the fourth one, it's 4 and then 2. On the fifth one, it's 5 and then 3 and then 1. And what you'll notice on the sixth one is the sixth one comes down and it has 6 on that diagonal, then it has 4, then it has 2, and then it has 0. And then on the 7th diagonal, when you draw it out, you're going to have 7, then you're going to have 5, then you're going to have 3, then you're going to have 1. And what you notice is that the even numbers, the even stairs, have an even pattern. And then the odd stairs, guess what they have? An odd pattern. Thank you all for saying that out loud. So odd stairs have an odd pattern. Okay? So we got odd stairs, odd pattern, even stairs, even pattern. And so what I'm looking at, if I want to go to the 14th, then it's going to be 14 plus 12 plus 10 plus 8 plus 6 plus 4 plus 2, and then we're done. Now, there's 1, 2, 3, 4, 5, 6, 7. So that's 7 consecutive even numbers. Okay, 7 consecutive even numbers. And if I have 7, that's an IV. If I have 7 consecutive even numbers, we have another problem that we've done that has a rule for however many consecutive even numbers and finding the solution. And the rule is going to be n times n plus 1. Pretty simple rule. So if I have 7 consecutive even numbers, my number of reds that are going to be in there, 14 plus 12 plus 10 plus 8 plus 6 plus 4 plus 2, is going to be 7 times 8, which is 56. So there's 56 red ones in this in the 14th staircase. All right, so those are two problems that are Mark Driscoll, his team. Of course, they cite others that originally did these problems. Here I am doing them too. They're great math problems. They're great for problem solving. They're great for challenging your students. And you can use technology like the iPad to help you challenge the students. Again, I'm Professor Lamb, and this is PiPad Mathematics. Take care.